I'm going to apologize if I seem a little bit off this morning. I am presently evicting a not very fun friend. Earlier in the year, I had a previous episode, and I named my friend that I was evicting Pebbles. This time, it's Schist. So, the good news, though, is this too shall pass. So this morning, I want to plug real quick Sarah, who kind of led us into, by talking about math behind computers, algorithms and data structures. If y'all would like to download the PDF, this will be back on later, but there is PDF available. Now, I will say the slides are a little verbose because you can use it as a study guide for those of you who are interested in algorithms and data structures. How many ever study data structures? Yay, awesome. So who am I? I'm a founder of the Making Software Greener, also founder of Sustainable IT Manifesto. The lovely caricature is from Star Trek, a conference in Columbus the first Friday in May. And if you get to speak there, you get a caricature. Quickly to plug the Sustainable IT Manifesto, we have a 4-step framework. You first start out becoming aware, then you become conscious, then enabled, and then empowered. And you can see our mascots here on the screen. We have the aware hedgehog, the conscious flutterby of transformation. We have an enabled fox because he's swift and smart. And then we have finally the kicks butt and takes no names tortoise of empowerment. Because once you're empowered, you can change the world. All right, why am I up here? Well, I started out having a Raspberry Pi problem. At this point, my data center in a box has over 20 Pis, gigabit switch, and so forth. I did not bring it on this trip. Wouldn't really fit on the airplane. But I was working at the time for a large not-for-profit in the data area of chemistry. And people were like, oh, those are toys. You can't do real work with those. Challenge accepted. So in cheminformatics, a substructure search is considered a non-trivial problem. If I'm going to jump in, I'm going to jump in. So that said, I set out to try and do substructure matching using the Pis. In the process, I discovered a lot of neat new algorithms and such. Now, I'm not a mathematician, I'm not a chemist, I'm not an expert, but I'm very passionate about this topic. Now, something to think about during the talk. There is one structure, one data structure that rules them all. It is used by every program in every digital computer. So, looking for answers at the end if you have any ideas. So why algorithms? Good algorithms really matter because either they break a problem into smaller problems, such as Sarah demonstrated yesterday, or they're myopic, they're short-sighted. They only care about their problem that they're solving. Now, there is no silver bullet. But as IT craftspeople, we really need to have more tools in our pocket than just a hammer. Because if you only have a hammer, you're going to brute force it. Now, putting on my architect hat, it depends. Sometimes brute force is the answer. Now, each algorithm has a sweet spot. It tends to be involved with space, runtime, or data access, for which one you want to choose. Step one, know thy data. No, this is not Socrates who said it originally. That said, data needs to drive every project. What the data is, how it's arranged, what's in it, what you want to do with it. Because everything that we do in IT is a data transformation. You know, we get one piece of data coming in, we want to do something else. That said, you wouldn't believe the number of times I've seen a project kick off where they start out by saying, without looking at the data, we're going to use this design pattern, we're going to use that design pattern. That's putting Descartes before the horse. And, you know, the data kind of flows by us, and, you know, once we've processed it and changed it, we can go on. So we're going to shift gears real quick. We're going to talk about the big O. No, not that one. We're going to talk about measuring complexity in an algorithm. You can also think of it in terms of the number of cycles that an algorithm requires in order to do its work. So we're going to start out first with linear time. Linear time, if you have one loop through, it's one cycle. 2, it's 2, 10, and so forth. The number of cycles is equivalent to the size of your data. Then we have quadratic time. 1 gives you 1 cycle, 2 gives you 4, and so forth. You can see that this is going to very quickly grow. And it's not a growth that you really want to have. An example of this would be the bubble sort. Then you have n log n, and it is faster because it is logarithmic. Then we have log n, which is faster than n log n, because we aren't multiplying it by the number in our of data pieces that we have. Using log of I, where I is some fixed digit, tends to be faster. And then finally, anybody remember Redwall? Yeah? So there was a character called Logalog. And so this is kind of how I think of a log of n algorithm. So if you look, for 100,000, it's taking 2 cycles. For 1,000,000, it's still taking 2 cycles. This is a real sweet spot if you can hit it. And we'll see an algorithm that approaches it in a little bit. But the real sweet spot is constant time. And I really should add another slide here about 4/4 and hemi, demi, semi time. So we're going to practice some different searches now. Let me tell you that these numbers were generated randomly. I did not fudge the examples. And the target number was also generated randomly from our available numbers. I really did not fudge it, and you'll see why I'm saying this in a few minutes. But a linear search. We start at the very beginning. It's a very good place to start. When you sing, you begin with ABC. Any rate, you all follow. So we start at 0 or 1, depending on your language. And then we go to the next, and the next, and the next, and the next, and the next, 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 next. And we're at 812. We found it. Now, sometimes a linear search is the fastest search because it doesn't have the overhead that some of the other searches have. If you're dealing with a very limited amount of data, 5 pieces or what have you, linear search is going to be easier to implement as well as easier to maintain. There's this idea of maintenance-driven development. And the idea is that 3 months, 6 months, a year, 2 years, what have you, you're going to get the call in the middle of the night. And I like to peg Norando here, not peg him, but call him out for his comments yesterday about documentation. And the other piece to it is if you're not to get the call in the middle of the night, the person who does knows where you live. So binary search. Binary search is a good algorithm because it cuts your search space with every move, with every cycle. So we're going to start out 333. We're going to go to 799. We're going to go to 876. And finally, 812. So we got there in roughly half the time that we had spent doing our sequential search. Then there's the galloping search. This one's really cool because it was published in 1976. And I, before starting to do this research, had never heard of it. Now, you know, with binary searches, we need to have bounds on both ends. Otherwise, it's really hard to cut something in half. The galloping search, however, is good for when the target's at the beginning or at the end, rather than starting in the middle and going back and forth. Also, if your boundaries are not closed. And it approaches O of log of I. So let's take a look at it. We have a sliding window. Our first window is 2 to the first, log. Our second is 2 to the second. Our third window is 2 to the third, or to the end of the array in this instance. When we find a proper window that our target is within the bounds of, then we do binary search from there. Now, if 22 is the target, this could be a case where it beats binary search. Binary search is going to take 3 checks, and the galloping search gets it on the first. Now, if we're looking for 13, binary search takes 4 to find, oh, it's not here. Whereas the galloping knows immediately. So like I said earlier, it's good for things at the very beginning, things at the end. Now, there are some variants. One is where we start from the end and work our way forward. Another is called the trot. It's a little slower, but we grow by 1 and then 2 and then 3. So our indices grow smaller, but if we have some idea of where the data might be, we can get there faster. And then once the value is overshot, we can then do O of square root with the, square root with the binary search. But what if we want something even faster? You know, everybody wants something faster, right? Cut down on your cycles, cut down on your processing time, cut down on your costs and your environmental footprint. So we're going to talk about the interpolation search. Now, when you look for a word in a dictionary, do you start in the middle? No, you're going to make a guess, right? You're going to guess that, it's about here. So you open up your dictionary and then you course correct. You make another guess. So it assumes an even distribution of your data across the array. And it approaches log of n. Now, remember, I generated all these numbers randomly. And I chose our target randomly. So our predicted location is what we're seeking over the max over the size. And we got it in 1. Now, worst case, we're going to be about the same as a binary search. But there are those times where we can go at, if you pardon it, ludicrous speed. So if we're searching for our 812, linear took 10 cycles, binary took 4, and the galloping search took 4 as well. And then if, say, the data had been larger, it's entirely plausible that galloping would have been faster. And our interpolation is 1. We got it in 1. So interpolation is generally going to be the fastest search. However, it depends on your data. Everything depends on your data. Now, there's a new measurement beyond big O, where we are going to look as well, not just the number of cycles, but algorithms that run more efficiently. So big O measures time and space growth. Green complexity measures energy and carbon. Now, a pet peeve is that while most people are talking about carbon and energy, there's another resource, well, there's many resources, but there's another resource at runtime that outside of the global south really isn't being talked about. Microsoft is building in Phoenix a data center that is powered by wind and solar. Huzzah for them. But last time I checked, Phoenix is in a desert. How are they going to cool their data center? There's not a whole lot of water there, is there? And most of what water is there is promised to people downstream. So there is definitely issues beyond just energy and carbon. So to compare, our big O focus for time complexity is CPU and GPU. But from an energy standpoint, how much energy are we using during the task? There are some newer GPUs that are coming out that are not 780 watts apiece. And some of those servers out in the cloud are having 32 GPUs at 780 apiece. That's no small bill. That's on the order of 24 megawatts, or not megawatts, kilowatts per hour. Just a little bit. For our deployment, we're going to look at the scale in N for our big O, and then total carbon cost. And then finally, in the terms of the context, how much is our hardware? What's our locality? A few years back, a government in Scotland wanted to be more green, so they decided to go to the cloud. All of their data centers ran off of wind and wave. But our new data center was in London and coal-powered. So when you are doing these things, when you're doing your research, you really want to and need to ask yourself, are we going to be better off? And the other thing, of course, is it costs more. So we want to use both efficient algorithms and efficient data structures. We want to keep our data as local as possible, because the network draws power too, and so does storage in your SAN or in S3 or what have you. Those all cost electricity. They also cost raw resources. A laptop, a 2 kilogram laptop, requires 400 kilos, almost 900 pounds of raw materials to make. So the next time you go out and buy a laptop, you might want to think about that. 85% of the total environmental footprint for cell phones is manufacturing. The electricity that it uses is negligible by comparison. You want to also avoid over-provisioned. Now this is going to save you on money, which will make the CFO and FinOps people very happy. And if you come from a DevOps environment, you know what? Measure all the things. So if you make a change and it's costing them less money and you can measure it, say, hey, we just did this for you. we're saving you this amount of money, this amount of resources. And who knows, they might give you time to do more. A lot of it's, frankly, tech debt. So, the fastest algorithm in big O terms isn't always the greenest. So you want to optimize for both speed and sustainability. Or it depends. And you go to an architect and ask them a question, and what are they going to say? First thing they're going to say is, it depends. So I have some key metrics on how to measure them in here. I'm going to just gloss over them at the moment. Feel free to go back and look at it and email me if you have any questions. But we're going to shift gears into data structures. So there are some data structures not appearing today. First off, queues, because Americans don't know how to queue. And also stacks, because these are queues. So the first queue is a FIFO, and the stack is a LIFO. Last in, first out, as opposed to first in, first out. Oh, come on, Americans can't queue. Come on. All right, our first data structure, and probably the first you ever worked with, is an array. And so you have a piece of memory that has individual elements in it. Then we go from there to linked lists. Now the thing about linked lists is they're a lot easier to do inserts than our array. Because with arrays, you have to copy the memory and make sure it goes in the right place. And that's a relatively expensive operation. But if you need to add something to the end, you have to walk the entire list. Traverse is linear, and you can also think of it as a one-way street. Doubly linked lists, however, allow you to go backwards and forwards. Now there's a little bit of overhead here in terms of complexity, because you need to maintain your pointers. But if you need to go back and forth, then this might be a good option for you. Inserts are less complex in an array, but more than just the regular linked list. Appending is also a bit more complex because you now have two pointers that you have to maintain. But it's a two-way street. So if you have something where you want to shoot past and then come back, your doubly linked list might be of utility. And then there's ring lists, where when you get to the end, you go back to the beginning. The second verse is same as first. It's often implemented as a fixed size array, so oftentimes it's used as a buffer. The problem is, if you're using it as a buffer, that you might overflow the buffer if you put the wrong data in it. If it grows to the size that your buffer is not large enough to handle. And you can think of it in terms of now serving. So let's talk a little bit about trees. A tree, in theory, will be balanced. Now our inserts happen such that, say I was going to add in 124. Well, I'm going to start at 333, and when I'm at 333, well, is 124 less than 333? Yes. So I'm going to go to 47, and I'm going to say, is 123 less than 135? Yes. So I'm going to append down to the left of the 135. Sorry, I had to think about it for a second. And add the 123 in there. Now, we're going to take a moment for a mini quiz break. This is from one of my favorite books. It's got lots of development and programmer puns in the series. And basically, two people are trying to maintain somebody's code, and the original writer of the code was kidnapped. Another possible thing that can happen. Also, too, try not to work on a project if you can avoid it where there's a bus factor of 1. The bus factor is how many people can get hit before you have a problem. So if you're the only one on the, on the project, that's bad. But basically, this algorithm takes the value of a string, multiplies them by a number, adds a number, and then divides by 65353. So let's take a look at this. We're going to add together the characters of the string. These are the ASCII values for Carolina Code Conference 2025. And there are all the ASCII values there. So we add them together, and we get 2084. Then we're going to multiply by 815. Anyone know why? 815? What's today's date? Today's the 16th. So we start with 815, and then we're going to add 816. And finally, we're going to integer divide, not floating point divide, our number by 26. So any guesses what data structure this might be? Anyone? Yes, it's a hash. So typically, your hash are used for sparsely populated universes. Gives you a very quick ability to look up values, and generally, or traditionally I should say, it is of a size of a relatively large prime. 65353 is not the largest prime number in a 16-bit unsigned integer, but it's easy to remember. So let's look at a hash. No, we're not going to use one that's 65353 elements long. That would take forever. But here's our empty hash, ready for data. And in this case, we're going to use a CRC to calculate a supposedly unique ID for the value that we're going to set things in. And we modulus it by the array length. We put some stuff in. We're going to try and insert 23, but it collides with number 5. Collisions are bad. We don't want to have two things trying to take up the same space. So what are our options? Well, an easy one and an expensive one is to rehash everything with a larger hash, or otherwise change our hashing algorithm if what we have is already sparse. But this is expensive because we have to run numerical calculations for every single element in the hash. Or you can use a bucket. So with the bucket, we have our collision, and we have created a linked list off to the side, so that once we have our collision location, we can then find all the values that match to it. And you see here, we've got several collisions that have happened over time. Now, eventually, the Lolrus steps in, and his bucket's full. You know, if you remember, one of the problems with linked lists is you traverse them linearly. So if you end up, having a bad hashing algorithm and, lots and lots of collisions, then the speed of your hash for both lookups and insertions is going to get very, very slow. And this is a problem. So how can we solve this? Everybody familiar or heard about the cuckoo? Now, so the cuckoo lays its eggs in other birds' nests and expects that they're going to raise their kid for them. One of the things, though, that the cuckoo does is it hatches earlier than most other birds. And it wants to have all the attention to itself. So the cuckoo kicks the other eggs out of the nest. Now, how would we apply this to a hash? Well, we try to insert 23 again, and it collides with 5. So we kick it out into another hash. So time passes, and we have some elements in both of our hashes. And then we're adding 101. And it collides with B, and when we try to put B into X, well, we have another collision. So we can try moving X back in, and X may very well go back into where we want it to. Because, as time passes, elements are going to be added and or deleted. Now, advantages. It approaches O of 1, constant time for inserts, and constant time for our lookups. And you don't get much better than that. Unless, your constant time is an hour, but that's another matter entirely. Now, it needs a certain amount of empty space. Otherwise, an eviction cycle can occur. And with the eviction cycle, we have here our 101 colliding with B, colliding with X. And so you can actually get a loop. So you want to, when you are doing your lookups, do a check and see, have I looped? How many times have I looped? And so once you've done that, then you need to resize and rehash to keep evictions from looping. And again, resizing and rehashing is expensive. Now, do we have a solution? Yes, we do. There's another data structure. It's the peacock. And it is very proud of itself and wants everybody to know about it. Anybody ever hear of a peacock hash? Well, now you have. So the peacock hash says, if one extra hash is good, well, we want more good. We are going to add other hashes. Originally, this algorithm was devised for network routers for doing IP and MAC address lookup. Network routers and switches that handle millions of inserts and lookups every second. That's pretty impressive, I think. So here we have our peacock hash, and we notice that we've had a couple collisions over time, but we're still running, and we're not getting into an instance where we have to rehash. So this one is constant time for both inserts and extracts. The other thing about this is, in the research that they did, they only needed 4 or 5 extra hashes. And if you notice, each extra hash is smaller. Now we're still using more data or memory than we might otherwise, but we are assured of constant size. And in that final hash, they found that 10 elements was more than enough. So it shrinks very, very quickly. You're not going to have, especially in a targeted environment like a MAC address cache. It depends on your data, right? So let's talk about sets. First off, unordered sets. A lot of languages use unordered sets as their only type of set. Python's one of them. And inserts, just throw it on. It doesn't care. It could be a list. It could be a hash. You could add it at the very beginning. Because you're unordered, it doesn't matter. But depending on the type of retrieval that you're doing and the type of data structure, remember, it depends, your retrievals may not be fast. The next type of set we have can be known as the Highlander set, where there can only be one of each element. So our elements are stored sorted, which means inserts can be expensive. So we have it here implemented as an array, and we're keeping our order. Anyone remember, the problem with doing inserts into an array is you've got those memory copies that you have to maintain at each time. Anyone have a suggestion for something that might be faster? Okay. I'm going to show that I am a child of the 80s here. Bueller.
Hash map?
A hash map would be a good one, yes. Yes. Or you might also use a list, depending. If you're doing a lot more inserts than retrievals, then having the list might work because there's less memory overhead associated with it. So one of the, shifting gears a little bit, one of the common errors that, and I'm going to pick on the new COBOL, Java, young Java programmers or inexperiences like hashes and hash tables and hash maps enough that they insert hash tables inside hash tables. Gets really expensive really quickly in terms of memory. If you have a good hashing key or a good key, you don't have to have multiple hashes. You can all have it in a single one. So here we have a linked list. That's one way to implement it. Or we could also store it as a tree. But there's a problem with trees. In an ideal world, our trees would be balanced. And so you don't end up with a situation where looking for a particular number, you have to go further down the tree. So if you notice here, 19 is the furthest down the tree. And to get there, we have to go through 1, 2, 3, 4 comparisons. Whereas 764, we have 2 at most. 47 or 135, we have 2, 1, 2, 3, or 3 rather, to be able to tell where to do the next insertion. So be aware of your data. Be aware of the advantages and costs of the data structures that you're using. And it depends on your data. The first few times I gave this talk, I would say, it depends on your data. And then I'd get people calling out from the audience, is this the fastest one? At which, of course, the answer is, yeah, it depends on your data. So, I would answer this, and they'd ask again. And finally, when somebody asked that question, the audience would holler back, it depends on your data. Getting audience participation is always good for us up front. Set intersections. When you have multiple sets, being able to find where the intersections go. Unfortunately, all of the implementations that I looked at use a linear algorithm for finding its set values of intersections. It doesn't care if you are trying to do a set and all the numbers in your first set are not within the bounds of the second. It still goes through and checks them all. Not very smart, is it? So, let's put on our thinking caps. Might there be better ways of doing this? Anything that we have seen today that might make it more effective for being able to look and compare the two sets? Well, we could do a galloping intersection. I recently, 2 years ago now, moved out to Colorado. And there's a town nearby, Estes Park. Estes Park is the town where the hotel from The Shining is. They're turning it into a museum now. But Estes Park has this really neat event that happens often, and they're called elk jams. An elk jam is where a herd of elk decides that they want to ignore the crosswalk signs and just cross in front of you. And elk are big. I almost hit one elsewhere. I was on a highway doing 65. It's about midnight, and I see this big amorphous thing going across the road, and I'm like, oh, is that a moose? No, it wasn't a moose. It was 2 elk. Oops, there's a third. Slam on the brakes. I'm here today, so I stopped in time, but it's an issue. Another weird thing for me, other than all the brown, I'm originally from upstate New York, and I've lived at one point here in Greenville for about a decade, but the brownness. But another thing is there is free range. Within the town I'm at, about 10 miles out, you start hitting free range. And there are black cows. So if you're not careful at night, there's a really good chance you're going to hit one. So this is numbers from a paper that compares different algorithms that are adaptive algorithms for doing our set intersections. And the link is live if you download the PDF file. But if you notice, our sequential comparison is about 1.2 million. No, about 12 million. Math is hard. But the adaptive cuts it down by about a third. And then other versions cut it in less than half. Yes?
Doesn't it depend on the data?
Of course it depends on the data. I don't remember off the top of my head exactly what data they were using, but they got it down to about 40% of the comparisons that they'd had. So adding in a little bit of intelligence means that you can take a poorly performing algorithm and increase its value, make it work better. Now, quick case study. If you recall, I have a Raspberry Pi problem. It's almost a Pokemon problem where I got to get them all. Or, if you will, I have ADHD. I'm not ashamed of having ADHD. In many ways, it can be a superpower, except obsessions. Whatever your newest hobby is, or what have you. And you go out and you got to have all the things and so forth. So, I started out looking for real work for my Pi cluster. And if you remember, I was looking at a non-trivial problem in chem informatics. So I start out with my Pi 2Bs, and the main limitation of the Pi 2B is its I/O. All I/O, whether it be network, whether it be reading from an SD card or over a USB, uses a USB 2 bus, which is limited to 480 megabits per second. Well, let's take a look. There's a database from the NIH called PubChem. I'm not sure if the site's live anymore after what's been going on, but compressed, the entire database is 150 gigabytes. Now, you uncompress it, it's about 3 terabytes. Not all the data is needed to do our analysis. There's a lot of things that basically include the energy across bonds in the molecule and so forth. Stuff that we don't care about. So first thing that we're going to do is make our search space smaller, right? So we're going to do an extraction of all of the structure information. And we end up with about 69 million substances. Now there's this thing called SMILES. SMILES allows you to textually describe data structures? No. Chemical structures. I've got data structures on the brain. Typically in the smiles, it does not include hydrogen. It's assumed that they're there. But a problem is, and we're going to ignore this for our first implementation, there can be more than one way to describe the same structure. So that's a problem. And here we have a benzene ring. Anything that, or most anything that's aromatic that you can smell has benzene in it. So, naive, but it might be good enough. Sometimes the naive that we can throw against the wall, test it in a very short time, might be good enough. So what are we going to use to search text? Any Unix folk out here? Well, yes. We're going to use regular expressions after a fashion. We're going to use grep, which uses regular expressions. And I'd like to plug Dustin with his regex talk later. He's actually closing out the day, so be sure to be here for it. So, naive solution. I built a Docker swarm with 5 pies, and they're each searching a subset of the data. So they each have a portion of it, which consists of an ID, the smiles value, and a name. And keeping it simple, because this is our naive solution, we're going to have it be a CSV type file, because we're just looking for a line, and it can chew through it pretty quick. Now, pat myself on the back. I was the first person to get Docker Swarm running on the pies. So I made an announcement of it, and my website fell over. So here's a couple tests that we did. And I was doing them live, of course, because I'm a masochist. And the first one, I'm looking for a benzene ring that has a double bonded oxygen off of it. And it turned out that out of those 69 million records, there was 2,500. Now, all of our reads are happening over the micro SD card, and those, of course, are known for their blazing fast speed. Not. If I had loaded everything into memory as a virtual disk in memory, it would have run a lot faster. And so in about 5 seconds, we got an answer. And for the equipment, I could have scaled it horizontally to get better results. One time, though, I was doing a live demo. And if you notice the difference between the two, I have a double bond in the one and a single bond in the other. Well, single bonds are a lot more common, but I'm doing a live demo here, and it's not coming back, and it's not coming back, and it's not coming back. Every presenter's nightmare, right? Oh, it broke. But it came back in about 15 seconds with 17,500 results that were gathered up by the master who had kicked off the job. All right, so that's my naive solution. PubChem has a defined bitmap that will describe a molecule. It's 880 bits wide. An example, one of the bit is more than 2 carbon or more than 4 carbon. So properties of a molecule will get matched here. So if you have something with 4 or 6 or 8 carbons, both the greater than 2 and the greater than 4 will be matched. It could also say this molecule has boron in it, or this molecule has a ring. Smiles, which has the shortcoming of having multiple ways of describing the same compound, can be converted to this fingerprint. Now, if I have sets of substances which each have a particular bit set, I can then take the intersections and find my matching. Now, so we have a set. We could do it by 810 sets, one for each bit in the bitmap, using one file per bitmap containing a list of substances which have the bit set. Our median size is 9.3 million, with containing about 232,000 substances in it. The average file size is 40 megabytes. Our entire data set then is 33 gigs. So this is why I was looking at set intersections and trying to make them faster. Now, one optimization, memoization. Why reinvent the wheel? If you've done a calculation once, save it. Don't do it again. You know, this is going to save on speed of execution. It's going to save on your time that you use, your energy, etc., because you're not doing the same thing over and over again. Another thing we can do is start from the smallest set and compare it with other sets. If the majority of the substances have a particular property, like has more than 2 carbon, for instance, then flip the bits. Check against the substances which don't have that property. Then you can limit your space. If it's a bitmap, why aren't we using bitmap tools? Well, I tried it. In order to fit our universe, which has 880 potential bits, we need a space that's 10,000 by 10,000 1-bit PNGs. They're from 12 kilobytes to 2.5 meg roughly. So here we have some bitmaps that were generated. And at the time I was doing the testing, I ran ImageMagick in a single core, because ImageMagick only uses a core. And unfortunately, if I were to use 5 cores, I'd get 30 a minute, which would take, if I were pre-calculating, over 20 years. So the bitmap really isn't that great of a solution. The other thing with it too is there are some things we're never going to try and match. So as a result, you know, why pre-calculate everything? All right, if you remember, I had said at the very beginning that there's one data structure that rules them all. Anyone want to take a stab at it? It's used in every program. It's used in every digital computer. Yes?
Bit.
Good, not what I was looking for. I was looking for something a little higher level.
Linked lists.
I'm looking for something lower level.
Heap.
Nope, I'm looking for something lower level. Pardon? Nope, not a, well, yes, stacks are used, but I'm looking for something even lower than that.
Pointer.
Not a pointer, an array.
Yeah, right.
Because memory is an array. And all of these data structures can be built on top of an array. I actually consider it a very good practice to go through and implement all of the basic data structures in an array, because then you understand how they work. So I use a tool called MarkDeep Slides for this. It uses MarkDeep for its rendering and makes the diagrams and everything like that very simple. I'm editing text. So at the end of the PDF, there's resources, 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 and more, and more, and more, and more. And thank you. Here's the QR code if anyone would like. I'll leave it here. Thank you for your time. Thank you for attending. Thank you for coming to the conference. And rather than applaud me, let's applaud Barry.
And now let's applaud Matt.
you.